All right, welcome back to Computer Science 50. This is the beginning of week 6. So on today's agenda is a little chit-chat about forensics, about JPEGs, about bitmap files, and ultimately about linked lists. But as is our tendency, first, perhaps something stupid.
Cats. Captions, like reason and argument, poetry and prose, or wine and cheese. A simple combination that we today take for granted. But the phenomenon known as lolcats has always been with us, since the dawn of time. Many people incorrectly assume that the cat macro, or lolcat, first appeared on the internet. But this is simply not the case.
The Bast tablet is what most macrologists agree is the very first example of a lolcat. It's a beautiful carving of the cat god Bast, holding a palm frond and stepping on a snake thing. And beneath it, we can read a phrase that crudely translates into, "I see what you did there." Hilarious.
And of course, that's not the only recorded instance of an early lolcat. Indeed, human and lolcat development often paralleled each other.
But by the age of enlightenment, humans began covering up their lolcats. X-ray analysis of some of the most famous paintings revealed some startling discoveries.
As the result of anti-kitted discrimination, we were literally being written over. But all that changed with Happy Cat.
When Happy Cat posted his picture on this new internet, it was the opening shot in the battle to bring lolcats back into view. Sadly, it was not the only shot fired.
Happy Cat was killed while lounging outside a motel room in Memphis. The assassin is still at large.
Happy Cat was a huge loss for us, but it was also a huge gain for the movement. Although he may never has that cheeseburger, he can rest easy knowing he's opened the floodgates for lolcats and the occasional wars.
Today, 26% of all emails include a lolcat photo. Happy Cat's dream was a cheeseburger, but he'd probably be pleased with this, too.
Attack of the show, weeknights at 7, only on G4.
So my thanks to the teaching fellows for discussing nothing else over email the past few days than that particular internet forward. So there is some more interesting news certainly in the world. This again is this popular news, geek-oriented news site called Slashdot. And I thought I would pull up just a couple of snippets, because if you start to take an interest in this kind of news, you start to understand, perhaps after taking a class like this, more of the jargon, certainly more of the topics that are covered. This top one seems to happen every 4 years and everywhere in between. Voters say machines are switching votes. So if you actually read through this story, you'll see that a couple of places in West Virginia County are claiming that people push one thing and they actually vote for someone else altogether. And if you kind of read between the lines, this can be certainly one of those things, one of those problem exists between keyboard and chair, this time being a user in front of these voting terminals. But it's actually really pathetic that 4 years later, 8 years later, the more and more municipalities that switch to these electronic voting machines can't get simple adders right. I mean, there's little more of these machines than a machine that has to implement ++, which is something we certainly covered all too long ago. There's some other perhaps relevant news. Those of you who actually have Wiis, Nintendo's homebrew blocking update hack. So this is actually representative of the so-called arms race that exists in the world of computers and computer science between black hats and white hats, or the bad guys and the good guys. You see this in a whole bunch of contexts, whether it's some company like Adobe trying to prevent you from cracking their Photoshop software, to a website trying to prevent you from accessing an account that's not actually your own, to Nintendo trying to prevent you from running software that you wrote or that someone else wrote other than one of their certified vendors. So long story short, there's been this history both with the iPhone, with the Wii, of people figuring out how to exploit bugs in the Wii, in the iPhone, so as to take it over. And what this article is about, for instance, is the fact that just as the Black Hats gained ground and were able to install whatever kind of software they wanted on their own personal Wiis and make it available to other people, well, Nintendo responded by updating all of our Wii's firmware. I myself updated my Wii last night, and apparently now I can no longer use this kind of software until you then read the article, which then discloses that the Black Hats sort of one-up Nintendo, and ever since this update was actually released, now can people actually continue to exploit the machine in ways Nintendo did not anticipate. So it's this perpetual arm race. But the funny thing is, or the interesting thing is, that many of these exploits boil down to the very basic things we've been discussing, or even the more sophisticated things like memory management arrays, because ultimately it's when people make mistakes that their software behaves in ways unintended, and that's when people can take advantage of you. So perhaps take an interest in that kind of stuff if it interests you. A couple of announcements. One handout for today, some slides and some code. Quiz 0 is this Wednesday, same time, not same place. It's in 3 different locations on campus. We will post a reminder on the course's homepage by tomorrow, but also check out that handout called About Quiz 0, which is on the lectures page of the course's website already. And even though Problem Set 5 is not due for 2 weeks, we thought that there's certainly some of you who love to get going early. So Cato will hold his walkthrough as usual tonight at 6 o'clock in Northwest Science B101. It will be filmed, so those of you who can't imagine beginning the problem set just yet, that's fine. Just know that the video will in fact be available. So a word on problem set 5. So the focus of problem set 5 in a C sense is to focus on file I/O, file input and output, and actually having you grab bits from disk, read them into memory, and do something interesting with them. There's several different parts to the problem set, most of which, beyond being related to file I/O, are related to multimedia, specifically the BMP, bitmap file format, and the JPEG file format. Any of you who've ever run Windows XP might remember the default wallpaper, the blue skies and green grass, the rolling fields. Well, that's an example of a BMP, a bitmap file, and it's generally an uncompressed file, which means that these things are pretty big, but they're also pretty simple. Microsoft sort of pioneered this format way back when, and even though it's evolved over time, a bitmap file pretty much boils down to a bunch of bits on disk that from top to bottom, left to right conceptually, represent each and every pixel in an image. And you simply store a different sequence of bits to represent the color of each of those pixels. And what this lends itself to is manipulation by software that we ourselves might write. So if you take a look, once you've begun the problem set, in the distribution directory that we make available, you'll see that there's this little guy. This is a little BMP file that I myself made by hand with a legal copy of Photoshop by clicking on the right types of pixels in the right color, but it's pretty damn small. So it's 8 pixels by 8 pixels, which clearly shows up quite small on the screen. And one of the challenges of this problem set is to write your own software that will enlarge a bitmap into something that's twice as big, 4 times as big, up to 100 times as big. So if I go ahead, for instance, and run the staff solution on this same file, what I'm going to do is run our copy of resize, which we've already written, a factor increase of 100. I'm going to run it on the file called smiley.bmp, and I'm just going to give it a new name called new.bmp. And if this program's written correctly, it's going to run pretty quickly. It's then going to dump into my directory here a file called new.bmp. If I go ahead and open that up, what I have created out of 8 by 8 pixels is something that's even happier than the original version. And so that is one of the programs you will be writing for this problem set. In addition to that, our hope is that you will take a little stroll on campus ultimately. So my MIT buddy and I indeed took our stroll after, what was it, last Monday or last Wednesday's lecture. It was a little awkward because we bumped into multiple CS50 students on our stroll, which kind of defeated the point of making it a scavenger hunt. But what we did was, using my friend's digital camera, we took 40 or so photographs. He did, really. He's the one with the skills. I just kind of pointed and said, that would be good. And we captured these photos on a compact flash card. So what I'm actually doing right now is completely lying. This is not a compact flash card. Any of you who know a little bit about cameras, this is a micro SD card. But I thought it'd be more impressive to show you my card than his because it's tiny. This is a 2 gigabyte card. I see our camera is trying to zoom in, but this thing is incredibly tiny. It's sort of like a fleck of chocolate. Ooh, double lie. 1 gigabyte as micro SD card. But the point is that we took these photos in some kind of electronic medium, this time called a compact flash card, which is a wee bit larger than this. And then unfortunately I got home and like an idiot, I formatted the thing before I actually took the photos off this card to make them available. And so having had a little bit of a background in forensics, having worked as an intern years ago in grad school for the local district attorney's office, I had some skills when it came to this stuff. So I put it into a Mac actually, which runs, you know, sort of a flavor of Unix, which lends itself to sort of lower level manipulation of data. And I ran a program called DD, which is an age-old Unix program that allows me to simply suck the bits off of the card, irrespective of what kind of files are there. It's just a stream of bits from the front of the card to the back of the card. And then I dumped a copy of those bits into a file. And I called that file card.raw. Raw denoting that this is just a raw file, bunch of bits. We uploaded that file to the cloud, and the third challenge of problem set 3, problem set 5, is going to be to recover these photographs for us. So you will need to learn a little bit about what the JPEG file format is underneath the hood. Turns out you can identify JPEGs by way of what's called a signature, patterns of bits that always should appear at the start of a JPEG file so as to sort of provide hints as to what's inside those files. You're going to leverage that information and, much like a forensic investigator would, in fact, write software if needed, or these days buy commercial software that does the same thing, recover those photos. And if you're the type who likes a stroll, likes a bit of competition, you and your section mates are hereby challenged to take a similar stroll around campus, identify the persons, places, or things that we photographed, all of which were meant to be identifiable but non-obvious. And if you go ahead and take a photo of yourself and or someone else in your section, thereby proving that you were in fact there, and upload those to a Google map with a place mark so that we know where you found it, we will have an amazing prize distributed to the section who finds the most such locations and takes the most such photos. So more in that in the problem set. So it's great fun, and we hope that you find this a very real world application of some of the fundamentals we've been covering thus far. And in fact, it's funny, ironically, it's this same friend who took these photos that 3 years ago asked me to recover photos for him from literally this, a compact flash card that he didn't accidentally format. It had just gotten somewhat corrupted. And so we similarly whipped up software like this 3 years ago and recovered like 95% of the photos, which was pretty good. And you guys will be able to recover 100% because we only formatted an unimportant part of the disk, but it at least makes it a little tricky to get at the data. So without further ado, here we are, linked lists. So here we are, ready now, linked lists. So what is today all about? Well, finally now in week 6, we can get a little more sophisticated than we have been in weeks past. So thus far, the problem sets have certainly had an element of design and thought to them, but many of you probably are just now getting comfortable with more of the basics. Not that a for loop or a while loop was ever that hard, but now the sort of stupid mistakes that you might have made early on by omitting a semicolon or not sort of incrementing the right variable, those kinds of things become very easily caught nowadays. And so you sort of have the ability, and dare say comfort, to tackle more sophisticated problems. And so what we do now in the course is introduce much more of an element of design. In fact, problem set 6, to be released in a couple of weeks' time, will challenge you to implement the fastest spell checker possible. And we're going to give you, again, a file that's got some 100,000 plus words in it, and you're going to have to decide for yourself just how can you most efficiently store all of those words in RAM so that you can get at them quickly when we then pass your program a series of benchmarks. For instance, a work of Shakespeare, the King James Bible, and some other smaller and larger sample inputs that we challenge you to spell check. And what we're going to do is clock or time the running time of your code, and actually, if you opt into this process, maintain a ranked list on the course's website for a week or so detailing exactly how fast each of your implementations are. This is, to be sure, something you can opt out of, but it's the only time in the course where we sort of foster or encourage a little bit of competition for the sake of just driving you to stay up 1 hour later to one-up yourself and improve your own running time. But a huge element of this problem set set is going to be that of design. In fact, your first implementation, if you're like me, if you're like a whole bunch of students last year, is going to plop you really embarrassingly down low on the benchmark list, because your spell checker might take 200 seconds to run, whereas the fastest one on the list last year was like 3 seconds or 4 seconds, an order of magnitude faster. But the funny thing is with this kind of stuff is that you can very easily chip away cycles, chip away at the running time of your code and whittle it down into something very tight. So it's all about furthering that kind of intellectual stimulation. But this begs the question, how do you go about storing arbitrary pieces of information in memory? So we started this last week when we had those structs. So a struct, sort of in English, what is it? What is a struct? What do you got? Sure, so it's a placeholder, or let me use a different word, a wrapper for a whole bunch of variables that might have some conceptual relationship among themselves, and it's either programmatically convenient or conceptually convenient to just kind of lump them all together. So we did this in problem set 4. What was a good thing, a positive thing about the fact that we lumped all of those global variables inside of a struct called G? Give me anything. What's that? You can add more, and it was sort of a clearly delineated spot where if you needed an additional global variable toward the end of implementing this game, it sort of fit nicely into the existing framework. What else was useful about the existence of G, as opposed to, by contrast, just having 6 or so global variables just at the top of the file without that wrapper? Yeah? So say once more, so you can use the same names? So you can use the names of those parts of it for local variables. Okay, so you can use its member variables as themselves global, but it's clear, if I can elaborate, throughout your program that this particular variable here is in fact global, just because we adopted the convention of calling the struct G, and so anytime you reference one of these globals, it was g.foo or g.bar. Now, arguably, we didn't need to do that because it didn't gain us any capability, but in that case, we decided, you know what, this sort of makes for a cleaner design. But there are certainly situations in which the motivation for structs is more clear. When, for instance, you want to implement a program that stores, say, a database of students. Well, it would kind of get annoying, if not a little difficult, to maintain, say, an array for just students' ID numbers, and a different array for students' names, and a different array for students' GPAs, and a different 2D array for students' grades, right? You could kind of assume that, all right, the ith location in the names array also belongs to the ith location in the grades array, which is the same student as the ith location in the IDs array. But conceptually, there's no sort of linkage among those separate arrays other than your own memory that I better index into all these different arrays at the same place if I want to get the ith student's information. It's much cleaner conceptually and programmatically if you can say, you know what, I just want one big array containing a bunch of student objects. And inside of those student objects, can you plop any piece of data that you want? A char star for a student's name, an int for a student's ID, another char star for their house. And it's a much cleaner approach because you can build on top of these primitives, ints and char stars and doubles, and build more interesting structures on top of them. But there is a catch. So suppose that we're implementing a database of students, and this is something that would be used by like FAS's registrar to keep track of all the students on campus. We can certainly do this with an array. But what are the implications for the size of the array and for memory management if we use an array to represent all the students on campus? Like, what are some of the worries that might come to mind if using arrays to implement a registrar's database? Yeah? Yeah, exactly. You've got to pre-allocate the memory if you use an array. And even though Harvard has, what, like 6,500-ish undergrads, well, some years there are more, some years there are fewer. And so you either end up with too little memory or too much memory, which arguably has some upsides and downsides. So what's been our approach thus far? If you have insufficient memory for the 6,501 students that enroll this year, what's your recourse? What do you do? Yeah, so you go back to your source code and you change the constant, probably at the top of the file, called num students to 6501 instead of 6500. Or if you want to be a little more careful, you might bump it up to 7000. Who cares? I don't want to go through this process of recompiling my code again. Let's just round up to the nearest count of 500 or something dramatic. But now you're just wasting memory. And even that's a little clunky because if the school ever does expand further, for instance, maybe into Alston, then you kind of have to dig up the source code, which by then, who knows what language is going to be in vogue. It'll become sort of the Fortran or COBOL as it was in the, around the Y2K problem. People don't want to have to go back into code that's 5, 10 plus years old because it's a pain to maintain. And there's no reason to, because we finally introduced last week this ability to allocate memory dynamically. With what function? Yeah, so with malloc, do we finally get a bit of runtime flexibility? We don't have to worry so much about committing to certain details at compile time. We can instead wait until the program's actually running, hence runtime. But if we have malloc at our disposal, thus far we've pretty much only used malloc to allocate memory for just arrays, right? That's what getString did. That's what some of our sample code did last time. We used it to allocate space for more ints, for more doubles. But what we finally do today is try to take things to the next level and design more sophisticated data structures that allow us to solve problems much more complicated than ones thus far, and also as efficiently as possible. For instance, let's take sort of a very real-world case, but boil it down into something a bit contrived. So suppose that Google represented the billions of web pages in the world in its database by using a big array. So there's already a problem with growth of the internet, right? If they haven't sort of anticipated how big the internet's going to be tomorrow, or the web, they're going to have to go into their own code, sort of recompile and reload all those billions of web pages back into memory from left to right, so all contiguous. So clearly there's problems with that. But what about sort of Google's bread and butter, search? How much time does it take to search for, let's just say, web pages about flamingos, which start with the letter F? Right, just to kind of coax you along. Like, what can we do with billions of pages in memory stored in an array if we're searching for pages about flamingos? For who knows why. It's the first word that came to mind. So what can you do? Like, what are the implications here for performance? What's that? All right, so keep them sorted. Unfortunately, we've seen algorithms that are like n squared or maybe n log n. Merge sort, for instance, was one better than the things we'd seen thus far. But even in our simulations, which granted we could have cranked the speed up on, they were still, for large inputs, it would seem fairly large, right? N times log n, where n is many billions, that's still a pretty big number, a huge number of milliseconds or microseconds or even seconds. So what algorithm might we, so suppose though we sort of deal with sorting up front, even searching in an array that's sorted took us how long? So log n. So that's pretty fast, right? Because that let us take a phone book that's got, what, 4 billion pages and search it in just 32 steps. That's pretty darn fast. But bear in mind that Google has even more than that, presumably these days. And they're not just sorting pages by, say, the title of the page, right? They're able to search by keyword, any number of keywords, do more sophisticated searches. And so even then, log n is pretty slow, it would seem. In fact, even if we just pull up one of Google's search results page. So let's go ahead to go to google.com and let's search for lolcats. All right, enter. So no one really looks at this anymore, but 0.10 seconds, it's actually pretty high for what we just did. You'll often see numbers that are even smaller than this, but multiply this by the number of people searching on Google at once, this kind of running time adds up. And odds are they did not just search a really huge array that they are maintaining in memory using even divide and conquer, using binary search, because in fact you can do much better. In fact, suppose I claimed that there's at least one data structure that exists that could improve upon search to get it down from log n to something even faster. Like, what would be the ideal? You'd be living in sort of a search utopia if you could look up arbitrary pieces of information in what kind of running time? Constant time. So one step. Right? Maybe 2, maybe 3, but generally that's still pretty darn fast compared to even something that's logarithmic. And so we're not going to give you that today. Linked lists will not give us that. In fact, linked lists are, dare say, worse than Worse than arrays, because we're truly going to have to search through them generally from left to right. But on Monday, we get to something called hash tables. We'll take linked lists, sort of rip them apart into their most basic pieces, and then re-implement a more sophisticated data structure still. So that's sort of our computer science cliffhanger for today. Let's do something that's not as good. We'll build on it Monday, but we'll see that already this is more sophisticated than what we've done thus far. So this is what I want to do. If I want to represent an arbitrary amount of information, I'm going to need some kind of structure. And I've been practicing with this pen, and I put on a thinner tip, so my handwriting should be a little better. So if I have an array, the problem with this is that if I decide that the school is 6,500 students initially, and damn, there's one additional student enrolled, what's slow about the process of dealing with that situation? So here's an array of size 6,500. One more student enrolls. What does the registrar's code need to do if it at least doesn't need to be recompiled? What if it takes the approach of like getString and deals with it sort of on the fly? What's that? Yeah, so resize the buffer. So you can call realloc recall or malloc yourself. But the problem with this is if you've got 6,500 cells in an array, that's not terribly small. And one of the claims we made last week, and you'll appreciate with problem set 6 when you implement your spell checker, is that allocating memory is relatively slow because it involves help from the operating system. Anytime you call functions, called system calls generally, that involve assistance from the operating system, there's a whole bunch of overhead involved because you have to context switch, so to speak, whereby all of the user's memory potentially gets moved around, removed from the registers, the tiniest pieces of memory in a CPU, all of the CPU stuff that then gets loaded in, so he can do his thing, figure out where he's going to give you RAM from. Then when he's done and he's found the one pointer that he needs to provide you with, he gets swapped out, essentially. The user's code comes back in, and finally can you proceed. And so if you're doing this again and again, or for really large pieces of data, it doesn't tend to be all that efficient. So what can we do that's perhaps better than that? Well, if we know that there's going to be the first student in line is about to enroll, why not just allocate as much space as we need for that one student? But the next time, it's the next student's turn in line when they're registering, then why don't we go ahead and allocate a second chunk of memory for that student? And when the third student's turn comes up, a third chunk, a fourth chunk. But notice I'm actually drawing these boxes not necessarily contiguously. There's gaps between them intentionally to suggest that, you know what, these pieces of memory could actually be coming from anywhere, depending on where the operating system happens to pull it from. So for instance, I ask for one chunk of memory, it ends up there. I ask for the next chunk, ends up there. I ask for another chunk, it ends up here. Now why might you actually get this kind of fragmentation in memory? Describe a situation in which malloc might actually return memory that's in different places, of the right size, but kind of all over the place. Why might that happen? So other programs are running. So physically in memory, absolutely. Your memory is not necessarily going to be contiguous. Although most operating systems, besides using virtual memory to create this illusion of more RAM than you have, they also use virtual memory to create the illusion to your program that all the memory you're getting is itself contiguous. But even within your own program, can your chunks of memory end up all over the place in that little rectangle we keep drawing? So why might that happen as well? Why else might you get such fragmentation, do you think? Not other programs running, but so who else's code could you be affected by in terms of what memory is available to you? Your own program, right? If you have other functions, other lines of code that similarly malloc memory, absolutely could they be using, for instance, the space that's immediately adjacent to this chunk in memory. So in short, unless you call malloc with a whole bunch of memory all at once, if you call it again and again and again, you're not necessarily going to get memory that's back to back to back, especially if there's intervening lines of code of yours that are getting executed. So that sort of begs the question, how do you deal with this? And in fact, today's terminology, linked list, kind of hints at, and certainly the diagrams in your hands hint at, the solution you can take to this. And that's to sort of chain all of this memory together, right? If I just know that this was my first return value to malloc, why don't I just kind of remember by somehow chaining this together that this was the next one, and this was the next one, and this was the next one. So they're not necessarily contiguous, but in terms of C code, how can I go about implementing these links, these arrows? Yeah? It can be, the last piece of each element can be what? The address of the next one, right? So we introduced pointers the other day. So instead of just describing these boxes as these abstract squares, let's actually think of them as structs. And structs can have multiple fields, so an int, a char, a float, a string, but they can also have pointers inside of them. So for instance, for now, these boxes are just students. But if I carve off part of this struct and say that it's actually a pointer, well, what I can store in that member variable in that pointer is just the address of the next structure that I allocated. Because I, the programmer, know the address of every one of these blocks, at least at the moment in time when I call malloc. But if I need to remember them somehow, I only have so many options. I could do something weird like allocate an array just to store all the different return values of malloc. And you could do that. Like you could implement code that sort of takes advantage of that representation. But far more common is it to sort of build that linkage into your data structure itself. And so what we introduced today is this notion of a linked list, which could literally look as sloppy as that in actual memory. But it all sort of works out nicely and sort of appears to your code as one long list from left to right, because each of these guys leads to the next one by way of, again, those things called pointers. Well, how do we go about implementing this? Well, you can do it a bunch of different ways. The syntax looks a little weirder than last week, but here we have this use of the keyword struct. It turns out that if I want a structure to be self-referential in the sense that it points to another instance of itself, you do have to give it a name up here. So last week we did not have a word here because we didn't need to use it inside of the structure. But anytime you, again, want to have a linkage among variables of the same type, we have to give it sort of this temporary name. And so a convention people use is to give it something like an underscore or some other identifier altogether. And in fact, this probably isn't the best one because it can potentially conflict with the compiler's own internal variables, but we'll go with it for now. Inside of a student, or inside of a node at the moment, a data structure called node is apparently two data types, a number and then a pointer to what? One of these things. So this thing is just a box that looks, roughly like this. It apparently has two fields, one of which is how many bits? The n field is what? So it's 32 bits because that's an int. How many bits is this thing here called next? And apparently my handwriting's not all that improved. How big is this? Yeah, so this is 32 bits too. Because it's a pointer, it's 32 bits, no matter how big the data structure it is that it's supposed to be pointing to. So this is just a square that's total of 8 bytes, 4 of which are actual useful information, 4 bytes of which are sort of like meta information that are useful only to the extent that we care about remembering this list. What does it take then, if we take this approach of linked lists, to remember where this thing is in memory? In other words, step back. When you keep track of an array's location, what piece of information do you need to remember? Like, what is an array, effectively? It's the address of the first element, right? It's a pointer to a chunk of memory, specifically a pointer to the first char or the first int or the first whatever that's actually in memory. So if you sort of apply that same logic here, what does it take to actually remember where a linked list is in memory? Just the address of, again, the first element. It's not a contiguous set of elements, but that's fine. We just need to remember the address of the first such element, because by visiting that node can we find the next one, and the next one, and the next one. In other words, if this is conceptually our linked list in memory, where it's just got a whole bunch of arrows leading from one to the other, and incidentally, what do I want to put in the pointer field of the last one, probably? Oh, we could. OK, so I heard we could put the first one. What do we have to be careful of? This kind of makes it really easy to write a really bad implementation of search, right? Because you can kind of be chasing your tail perpetually. So if you have some way of detecting that, that's fine. But what might be simpler instead of just putting a pointer back to the start of the thing? Null, right? We need one special value that the world has sort of decided has special meaning. Let's put null or \0 there, effectively, or the number 0. All right, but what does it take to remember what a linked list is? Well, it turns out that you can implement a linked list with just one pointer, much like you could malloc dynamically an array. All you need to do is keep track of 32 bits, the 32 bits that describe where that thing is in memory. And what this allows us to do is, how do you go about implementing a linked list of size 0? What does it take? How do you implement a linked list of size 0? What do you need? Well, how do you implement an array or represent an array that doesn't really exist? Just the pointer to null, right? It's just nothing. So conceptually, the only thing it takes to implement a linked list is a pointer. And if by default, and typically one will draw a slash through something to mean that this is null instead of literally writing null, there's a linked list. Right? So we're sort of done. All it takes to implement a linked list, at least in the simplest of cases, is writing something like int star p gets null. Now unfortunately that's not quite right, because what is a linked list? It's not just an int, it's instead what? It's not a pointer to an int itself, but a pointer to one of these nodes. So we need to actually do something more interesting. So let's take a look. So if I go ahead and pull up list1.h, what we'll see is the following. So in list1.h, we simply have a formalization of that in a .h file. Okay, so no magic there. This is a struct that's 8 bytes big. It's got an int and it's got a pointer to the next such node. Now let's go ahead and open up list1.c. And if you glance at your paper, there's actually a whole bunch of code there, but much like Sudoku, if you sort of look at it piece by piece, it's all fairly straightforward. So we seem to have included a whole bunch of libraries so that we can actually use a demo here. I went ahead and used the CS50 library. I'm including my own header file, so I have access to that structure. But per my claim a moment ago, all it takes to implement a linked list is just a pointer. So literally, do I have in this program, though arguably it's a silly claim, a linked list, but by default it's of size 0. So what do you think it's going to involve if I want to add a student to this database or add a number to this list? Like, what function am I going to have to call? Right, we only have one function really to getting new memory. If I need a new node, a new wrapper for a number, I call malloc and I pass it in the size of one of these structs, one of these nodes. What do I then do now that I have a chunk of memory that malloc has handed me? And again, my goal is to input one number into this linked list, like the number 2. In fact, let's make this more real. So let me go ahead here and change one thing. In your printout, true and false were capitalized, though they should not be this semester. Okay, good. False isn't even there. So make list 1. Okay, good. Compiles. Let's go ahead and run list 1 just to make this more real. So this is just a quick and dirty demo program I whipped up that supports 5 different menu options. So this is another example of a wonderful loop, right? So let's see. I want to go ahead and find the number 3. Okay, nothing happened because it's not actually there. Let's go ahead and insert, by typing number 3 for that command, the number, let's say 10. Okay, so list is now 10, and there it goes up here. All right, let's go ahead and insert another number. So let's insert the number 15. Now one of the goals for this program is to maintain the list sorted, which will lend itself to an interesting look at how this stuff is implemented. Let's insert another number. We'll make this more interesting and dynamic. Give me a number. 13 I heard. So let's hope that it actually goes, and it does, in the middle. And give me one more if you really want to participate today. 27 I heard. So we'll go with that. And now the list is of size 4. So let's now roll back to the start of the story. Initially the list was of size 0, and that was implemented by way of a pointer that was initialized to null. Pretty darn easy. When I first ran the insert function, the insert menu option, and then typed in the number 10, what happened? Well, malloc presumably allocated how many bytes for me? So at least 4 hopefully, but really if we want to keep doing this and maintaining some structure, we needed 8. Now the first 4 of those bytes ultimately are going to have what put inside of them? So I got back 8 bytes, and I need to treat it as 4 and 4. What am I going to store inside the first 4 bytes? So whatever number I typed, so 10. So 10 is going to go in the first 4 bytes, but what am I going to put by default in the last 4 bytes? So a pointer, namely null, if this is the first such element. So this is why, again, it gets very tedious if you sort of think of things always in terms of memory and addresses. This is why the world does generally draw things as abstract pictures. This is 8 bytes of memory that just got malloced, assuming this is how this function is implemented. We're going to divide it conceptually into 2 parts, something called n and something called next. Next is initialized to null. In here, though, is going to go the value. And again, this is 4 bytes, this is 4 bytes. And my linked list, meanwhile, itself is a pointer called first, just to denote that this is a pointer to the start of the list. And it is pointing where exactly? That's kind of cool, actually. Where is it pointing? Yeah, so it's, all right, can't do that too many times. It's pointing, in fact, to, I'm new to this. It's pointing to the start of that thing in memory, the very first byte. All right, so now let's take a look under, oh, let's actually, while we're still running here, now someone else can participate if you'd like. What number would you like to find? What's that? 15, I heard. Found 15. OK, I heard 12, so someone's trying to be difficult. So let's run that. So find the number 12. Nothing seemed to happen. So it didn't actually say we found anything. What about if we tried to find the number -1? Nothing seems to happen. So at least there's some error checking there. Finally, let's do something somewhat more interesting. First, let's traverse the list. So 4 just walks the list and tells me what it is again and again. Doesn't do anything to it. Let's go ahead now and delete the number, just to be annoying, something in the middle. That's probably the trickiest case. 15. And it does seem to work. So the question now is how? So let's go ahead and type 0, go back into list 1, and see where the interesting aspects are. So the main routine is not all that interesting, right? This is the kind of stuff we mean should be getting much easier for you these days. So we have a do while loop, as you often do. Anytime you want to get user input again and again and again until they provide some sentinel value, like 0 for quit. We've got a menu that looks ugly only because I'm using all these \n, but it's just printing what we saw a moment ago. I'm using getInt to actually get the user's input, so that's familiar as well. And here's another instance of switch. So wonderfully useful for Sudoku. Similarly here, if you have a set number of cases that you want to handle, I even did it all in one line just because it looked a little prettier than indenting everything. So we have 4 actual cases, but otherwise this loop quits when I type in 0. But there's some interesting stuff that's going to happen now if we want to clean up our list. So free, recall, is an important part of cleaning up memory you've allocated. So we'll assume that we're going to eventually get to that. So take a stab. What's probably the easiest function to take a glance at first here? What's that? Did I say one letter? I heard traverse. The acoustics are a little difficult in this room. So traverse. So let's take a look. All right, so traverse is a void function because we kept it simple. How, though, just as a quick refresher, how was the linked list implemented? That's sort of the key insight here. That's it. One pointer, a global pointer in this case, called first. And it's a pointer to what? A node. And what was a node? Again, just to be sure one's following along, it's that, which is a little ugly looking, but it's just saying an 8-byte structure with an int first, followed by a pointer called next that points to one of these things. But again, just for arcane C reasons, it'd be nice if we could just say this, because it's a little clearer, but you can't. So you have to have sort of this temporary name built into the definition of the struct. So that's all that's happening there. All right, so back to the traverse function. It's the very last alphabetically. So let's scroll down here. What's going on? So traverse the list. We first print out something like list is now. Now I'm doing this. So this is kind of interesting. This would be called what kind of variable? Quick sanity check. So this is a local variable, but it's now a copy of the list. It's not copying the linked list per se, but it's copying what? Just the pointer. So this is equivalent to my sort of putting my finger on the same location in RAM as is that global pointer. Probably the motivation here is to not screw up what? If I just want to walk the list, what do I probably not want to change while doing that? First, right? Because if I keep updating the first pointer while walking along my list, that's sort of equivalent, you would think, to forgetting about what's behind you. So you forget about the first node, forget about the second one, until finally you reach the end of the list, and all you've got left, because you're using the same variable, is a pointer to the very last, which kind of suggests a memory leak. So we have a temporary variable here. And now this is saying, while pointer is not null, so this is like saying, while my finger is not actually pointing at a null pointer, go ahead and do what? So what does this first line appear to be doing, even though there's one piece of new syntax for most of you? Yeah, it's printing the number. That's it. So %d is an integer, prints out a space after that. Pointer is the temporary variable, PTR, but this arrow notation is probably new. And all that means you should be doing is what, do you think? So if you have a pointer and you want, and that pointer points to a struct, and you want to get at the piece of data in that struct, you don't use the dot operator. Instead, you use the arrow operator, which is actually kind of nice. Finally, we have a piece of syntax that's consistent with, for instance, the types of pictures that we tend to draw a lot. So the arrow operator means take a pointer, follow it to memory, and go to the member variable named n in this case. So we don't use dot, because dot actually suggests that this is a struct itself, but PTR, again, is a pointer to a struct. So that's the only distinction here. What's this line right after the printf doing for us? On line 236. Yeah, so it's just pointing to the next one. So again, if this structure is something that looks like this, and then the structure has something after it, and then dot, 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 and each of these things has a pointer, one of which points to the start of the next guy, and one of these guys eventually is null. If you have PTR, which is a pointer, which we draw as a little box, and you initialize it to point at first, that's like saying this is PTR. Meanwhile, there's another pointer in memory globally called, and apologies for the handwriting, first, which is pointing to the same location because the former is a copy of the latter. But the moment we get to this line of code here, pointer gets pointer arrow next. Well, next is this thing. So what value is here in the bottom? Well, this is just an address. Pictorially, we draw it with an arrow, but really this is like OX12345. And what does that mean? That means up here is like OX12345. So if I say pointer gets pointer next, that's like saying put whatever's in here, and this is going to be a god-awful mess in a moment, but the effect of that pictorially is to say move the arrow here. That's all. Point the pointer at the next field of the current guy. All right, so this thing goes for how long, this loop? When do we stop? Yeah, so you stop as soon as you hit the null pointer, which is this thing. So as soon as you reach dot, 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 the last guy in the linked list, and his next field, pointer arrow next, is actually null. Well, that's fine. You are going to set null to the pointer variable, but then the loop is going to terminate because we've hit the end of the list. And now why, even though there's a comment there, do I call fflush on standard out? The stream called standard out? It's just that stupid buffering reason, right? I don't have any \ns, nothing at all, so I need to force it to actually print something out. Now here's something interesting. Why am I sleeping in this program? Why am I sleeping? Recall that the function here, if we print the list program, if we insert the number 1, if we insert the number 2, notice how it's pausing. Why do I call sleep? It's just because I noticed while implementing this program, everything kind of scrolled up too fast to be interesting. So sometimes the answer is not, okay, now I realize myself, the answer is not all that interesting. The answer was just because. It made for a slightly more readable user interface. Won't ask that question next year. All right, so the find function. Okay, any questions first about traverse or what we're doing here? Because if you have gotten totally lost as to what a linked list is or how you represent it in memory, then this whole exercise is a waste of time. Any questions? Totally fess up if you're at all puzzled, or tell the person next to you to raise their hand for you. Okay, a few heads turn. That's kind of funny. Yeah. Ah, good. Okay, so that's actually, we might as well bring that up now. So yeah, so in the past, anytime we've done anything with pointers, we use the star operator, not just to declare the pointer, but also to dereference it, that is, go there. So in fact, you can do this. And this is another piece of syntactic sugar, so to speak. It just makes your life a little prettier, a little nicer. This line of code here, and I'll leave it on the screen and make a temporary copy, is actually identical to saying, go to the chunk of memory at pointer. But now just because I need to parenthesize this, it's going to look a little uglier. Go there, dot, n. So those two lines are equivalent, and they're maybe more consistent with what we've been preaching last week. Go to this address, then grab this member. The arrow operator is just a syntactic trick to doing both things at once. But if that helps you understand exactly what's going on, it's exactly the same. So this is a new piece of syntax, not anything conceptually new. Good question. Other questions? Yeah? Oh, why we called fflush? So we call fflush in a bunch of the lecture demos anytime that we think that nothing's going to print automatically. So remember that for performance reasons, functions like printf don't actually display what you've told them to print until you pass in a \n. So in this case, because I've never bothered to give the function a \n, it's just kind of waiting, thinking, well, the user can deal for now until I actually see a \n. But if I, the programmer, know it's never going to get that, at least to the very end of the program, fflush just overrides that sort of efficiency mechanism and says, whatever you've been buffering, spit it out now, because I say so, literally. Yeah? So clarify why we're using structs instead of anything else? So what's the alternative, I would ask? So that's all we got in C. There are no classes in C if you're coming from like APCS or a Java background. So structs are all you have. So really the only alternative here would be to sort of roll back a week, implement this list as an array that can just store ints, which actually in this case is kind of compelling because we already know how to do that. But we'll see in the next example when we move to version 2 of the list structure, when you start wanting to represent not just numbers, but for instance in list2.h, students, and a student might actually have an ID and a name and a house, then the use of structs becomes a little more compelling, if not a little more obvious. So we'll get to that in a second. Other questions? All right, let's look at this one other function here. All right, so find. What does it take to find? Well, find is pretty much identical to reverse, but what do you need to do at each step? Just check if the number you're looking for is there. So find's purpose in life is to ask the user, what number do you want to find? Store that value in a local variable called n. It looks like we then begin to traverse the list using the same temporary variable as before. We use a loop while pointer not equal null again, but we just have the sanity check. Instead of printing out each element, we instead say, does the current element being pointed at, field called n, equal the n the user cares about? And if so, print yes, sleep for a second, break out. Otherwise, go ahead and move on to the next element. So that's it for find. So what more is there to do? Well, insert is a little scary, but what about delete? What about delete? Actually, delete's a little scary. Let's go ahead and take a 2-minute break. All right, we are back. So I think that rather than look just yet at more lines of code, why don't we do things the old-fashioned way? Because I actually think it's perhaps more clear this way around. So again, the motivation here was to be able to store an arbitrary amount of information, whether it's 6,500 undergrads whose count you don't know a priori, or a whole bunch of numbers, which in this case is what we're doing for simplicity, or in a moment a whole bunch of students, including their name, their ID, and their house. So the motivation here is just to store a whole bunch of numbers. We're going to maintain them in sorted order ultimately, which is useful. But again, we don't want to sort of pre-commit ourselves to an array because one, we don't know in advance how many numbers we're going to need, and it's just a pain to have to go back in and recompile your code. And two, we don't even like the idea of using realloc or sort of rolling our own implementation of it by running out of a space in our array, mallocing a new one that's bigger, copying everything over, freeing the new memory, just because that feels like a lot of wasted energy. And in fact, it is. It's a waste of CPU cycles. So today is about doing better and being more dynamic and allowing your program to scale to, within reason, an arbitrary number of inputs, memory permitting. So let's suppose that I've been running that program for 5 different steps and I inserted like the number 22, 17, 26, 9, 34 in any order. And because of the magical insert function, which we haven't looked at yet, these things have been maintained in sorted order. But there's some other stuff going on inside the program, and malloc isn't necessarily returning to me chunks that are literally next to each other. So there are gaps between these structs in memory simply because of the way the operating system's been behaving. And to be clear, what is a node? To answer a question that came up during break. So if we want to have an arbitrary number of objects in memory, literally integers in this case, but we somehow want to link them all together, we need some kind of wrapper structure. And so we're going to call this wrapper, quote unquote, a node. And its sole purpose in life is not only to store the data, the int that we care about, but again, this sort of metadata, this stuff that's kind of necessary to keep track of everything, but isn't fundamentally that interesting, because who really cares what these pointers are? They're just utilitarian in this case. Now, to be technical for just a moment before I erase it, when malloc is called again and again and again and again, you get back these addresses, so byte locations in memory. And let's just say arbitrarily that this one is 1, 2, 3. This is like 4, 5, 6. Because they're not necessarily going to be increasing in order, this might be 3, 4, 5. This might be 7, 7, 7. And this might be 9, 8, 7. So these are just addresses in memory. And they could go all the way up to like 2 gigabytes, 2 billion. But we're going to keep the number small. So if a linked list is all about remembering where the next such structure is and remembering where the whole thing is by way of one pointer here, if I really wanted to be technical and say this pointer here called first contains the address of the first node in memory, what value literally is going to be stored in RAM at this location? So 1, 2, 3. So 1, 2, 3, and I'm intentionally writing small so I can erase it without making a mess, goes here. So what's going to go here? So that's the 4, 5, 6. This is going to be the 3, 4, 5. This is going to be 7, 7, 7. This is going to be 9, 8, 7. And this is just going to be 0 or null depicted with this slash. So that's really what's going on in memory. The problem with this is that you glance at this and it's certainly not obvious what's going on. And so this is why, even though this is literally what's going on with pointers, and that might actually have some kind of technical interest to some of us, what's actually more, I think, useful is, again, to rely on things that are more conceptual. Whoops, should have drawn that to the top of the structure. That are more conceptual than they are necessarily technically precise. So what we really have in memory is something that looks like this. Right? And ergo, we have a structure like this. The first field is called n, the second field is called next, and that is what we have in memory. What these folks have done here, because this is an excerpt from a popular textbook, is that's also sort of like grounding if you're an electrical engineer, just means that is in fact null. So this is the representation of a linked list in memory, the motivation for which is to be able to store an arbitrary number of ints. Nothing more interesting than that just yet. So what is involved in traversing a list? So this now is a much better prefab job than I can do with my little tablet here of how you go about walking a linked list. So this is that same linked list again and again and again, 4 times on the same slide. But what it's simply showing at each step in this picture is what was going on inside my own code. So when I said I had that temporary variable called pointer, PTR, that was initialized to the value inside of first, well, that's like simply drawing on the board just one other pointer that takes up 32 bits. It's called PTR. It's going to get the value 1, 2, 3 because that's what was in here. But again, pictorially, that's like saying point there. And so traversing the list, namely my traverse function, quite literally did what this picture suggests. It initialized pointer to the first element. All it then did was print out the node or PTR arrow n, because that's the value at the current node. Then it went ahead and updated the value of this element, which is here, again, 1, 2, 3. And when I do pointer gets PTR next, well, just ask yourself, what is inside of pointer next? Well, pointer next is what? So if this is pointer, and I'm pointing to next, that's like saying go to the element and go to its field called next. So this arrow corresponds to this arrow. That's all we're saying. So what is actually here? Well, precisely it's 4, 5, 6. So that means store in PTR what? 4, 5, 6. But again, pictorially, that's like saying, all right, clobber this arrow, clobber 1, 2, 3, and actually, at the risk of making it a little ugly, point to whatever that field was pointing at. So all that's happening in the traverse function is this 32-bit pointer, this temporary variable, is getting pointed at this guy, then this guy, then this guy, then this guy, then nothing, because it's being assigned the value 0 or null. So that's all that's happening in traverse until we finally sort of bottom out and hit, as this picture suggests, the null character. All right, so what more can we do? Well, now it gets interesting, and this is where it would get scary just looking at code, because there's several different cases you have to consider, and the slide kind of hints at these. But what would you say are the 3 situations in which you might actually have to have different pieces of code to handle it? Maybe 3 different if else constructs. You've got a list. You've got a list. Where might you want to insert the element? The beginning, the middle, and the ends, right? And they're different conceptually, because think about it. In the beginning of the list, it's sort of a special case because you've got nothing to the left of you, but a lot of stuff to the right. So you kind of have to wedge the new element in sort of a careful way. The end of the list is similar in spirit. You've got a whole bunch of things to the left of you, but nothing to the right. So you kind of have to tack that thing on to the end. And the middle is maybe the most annoying of all, because you have to kind of wedge this thing in conceptually in between 2 elements, and that's going to involve a little bit of careful thought, because right now this element's pointing to this guy, but now you've got to point this guy to this guy, and then this guy to this guy, and it's going to be very easy to sort of accidentally lose track of one of those arrows, so that you might have a very nice linked list that goes here, 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 and then if you screw up, this guy is left dangling, and now you have a memory leak because you forgot what the pointer is that was supposed to connect because you clobbered it by making this new element appear. So let's see how we can do this. So let's consider the middle step first. So this is the scenario in which I've been running the program 5 different times, inserting 9, 17, 22, 29, 34, and then I go and insert a 6th element, the number 20. So the very first thing my code is going to have to do, even though we haven't looked at the insert function, is call what function to help me out? So I need malloc. So malloc is going to be asked for, in this case, 8 bytes of memory. I'm going to get back ideally a pointer, and now I'm going to start treating that pointer as though it were a struct called node, which again has 8 bytes. It's defined to be 8 bytes. All right, so conceptually, what do I do now, without flipping to the next slide, to insert this thing into this list? Again, maintaining sorted order. How do I find its location, do you think? Exactly, iterate through. In fact, we as humans can sort of omnisciently see the whole list here on the screen, but so far as the computer is concerned, what is the only element the computer has direct random access to? Just the first, right? So we are sacrificing something versus arrays, right? Arrays were nice because you can hop to any location. You can do this very clever binary search, divide and conquer approach, because if you jump to a certain location in memory, it's sort of like a leap of faith that's going to be a good one because you know there's something there. With linked lists, you can't just go hopping around halfway between 2 nodes because nothing might be there, and you're going to touch a segment of memory that you don't own, and thus what happens? Seg faults, right? Core dump, bad thing. So insertion in middle suggests that we should start at the beginning. We're going to iterate just like our traverse function again and again and again until we detect that the current element is probably greater than the one we just looked at, but less than the one to the right of it. In other words, just with a couple if checks, we can probably find at least where conceptually this thing needs to go. So this new element, just to clarify, is initialized to just be a big rectangle with 2 blank fields or some garbage values. So we won't draw anything at all. If I want to insert 20 in here, after calling malloc, I'm indeed going to put the number 20 in the first field. What do I want to put in the second field, the pointer field? A pointer to the guy to the right of this node. So I've got to find, first of all, where this guy belongs, and it is in between 17 and 22. So now for the sake of argument, suppose that I know the addresses of both these elements, because I'm using enough temporary variables to keep track of them. I now know that 22 is at address 345. So what do I put in the bottom of this recently malloced chunk of memory? Yeah, so 345, or again, pictorially, an arrow to this node here, the 22. All right, what do I then need to do? And this part's actually not that hard. I can clobber this guy who currently contains the number, what, 456, and instead write in the number, whatever this is. We don't even know offhand because I've not drawn it, but conceptually, we're going to have just an arrow pointing there. So what values have I just clobbered? Well, whatever was in here, right, but this was junk, that's fine. This was junk because it was just mallocked. I did throw away, did lose one value, but not before it was too late. I just clobbered this value here, right, with the new pointer. So if you roll back in time, was it important or unimportant the order in which I updated some pointers? So yeah, it is. All right, it's kind of an easy question to answer, right? Because suppose that I allocated this new node, as this picture suggests, and we'll draw it again over here. All right, I put the number 20 in here, and suppose just because I like to think from left to right, I found 17, I know what the next one, I found 17, aha, 20 is bigger than that. Let me go ahead and point this guy here, and this is when you have that sort of, oh, like damn moment, I lost track of the pointer because I literally just clobbered it. So we need some kind of mechanism for remembering that. Either a temporary variable, like TMP, so we keep it around, or, like we did the first time, just do this step first. But therein lies a very easy way of breaking one's code. So that's what this 3rd step picture suggests. Tail is kind of easier. So if you discover by traversing the list and doing some inequality checks, is this greater than, less than, and dot, 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 you find your way all the way at the end of the list. Because PTR is null, what do you need to do to insert a new element at the end of the list? For instance, the number 55 in this example. What do you need to do? What do you need to update? So you need to point to 55. So what was previously null needs to become the address of the new node, and then what do I put in the recently malloced element, which again has 55, and what in the bottom? Just null. So that's it, as this same picture suggests. So the head of the end of the list seems pretty easy, tail. What about the head? Well, if you detect that, well, the user's trying to insert the number 5, and you check if n is less than the value of first arrow n, that is if it belongs at the beginning, well, what does it take to update this? Well, don't I just have to do first gets the return value of malloc? So I discover that the node containing 5 belongs at the beginning of the list. What pointer need I update first in order to squeeze him into this linked list? What's that? So I heard the word first. So suppose I do first gets the address of this new element. So if the address of this new element, for the sake of discussion, is at address 999, because it's way at the end of memory for now, and I've put in the number 5, well, this guy, should he be null? Well, no, right? Because he needs to ultimately point to the previous first element. But which needs to happen first? I then have this the first pointer, which I'll redraw here. So that's first. He's currently pointing to 9. So I have kind of a decision to make. Do I update this pointer first, or do I update this one? Right, you have to update this one first, right? I'll do it the wrong way. Here's first, it's pointing at number 9. I instead rewrite it here. Now I ask myself, what do I put here? You kind of just screwed yourself because you've clobbered the value in first. So again, order of operations, or you at least need a temporary variable. But if this looks a little cryptic, again, it's just kind of common sense, right? You've got a whole bunch of things laid out in memory. The thing is remembered by way of its first address. How do you go about inserting it? Well, you have to remember the address of the new first element, but not before you actually go and tack on to this new element the rest of the list. So that's how you might insert from the head. What about deletion? Well, deleting is also kind of interesting unless you use enough temporary variables or respect the right order. And in fact, as this picture suggests, and as the code you'll see does, actually uses a couple of pointers. One called PTR to kind of walk the list. But you'll see that I conceptually walk with my left hand one step behind my right hand. Because when it comes to deletion, I'm going to need to pull out, for instance, the number 22. But if I just go ahead and now update, for instance, well, how do you map around 22? Well, you have to set 20's pointer to be what? Sort of 29. But if I haven't remembered the guy I just freed, then you have, again, a memory leak. Because if you just lose that pointer by drawing only this arrow first, again, you're going to orphan, so to speak, one of those nodes. So we, again, need some additional storage. We'll see. Tail. Tails, same idea. In fact, the tail and the middle actually work out to be pretty much the same case if you implement the code in the same way. The head is a little more interesting because what does it take to remove something from the head of the list, like the number 5? Well, you do have to update first to point not to the first element but now the second. But again, as this picture suggests, you need to remember the address of the guy you just ripped out so that you can do what with him? Call free. Right? So again, sort of some basics that derive from the definitions we've looked at, say, last week when it comes to pointers. So let's take a look at this. So we were in list 1C. Let's go ahead and scroll down now to just the, what's not so bad, the insert function. All right? So, code ahead. All right, so what do? I have just invoked the insert function, which again, if you've forgotten what the program looked like this. I type the number 3 to insert. I insert the number 10. The list is now 10. So the question on the table is, what just happened? Well, the very first thing we did verbally was say you need to call malloc, and so we do. How do I know how many bytes to ask of malloc? Well, again, you don't probably want to hard code 8 probably, because we can be a little more dynamic. So we use that size of operator, and we say, give me enough memory that fits the size of a node. Now I do the sanity check. If this new pointer comes back null, that means I ran out of memory, something's broken, quit. Don't try to dereference that pointer. Otherwise, go ahead and ask the user for an int using getInt. But notice what I'm doing. Where am I putting that int? So where am I putting that int? Well, if the structure looks like this in memory, and again, this is n and this is next, where am I putting the return value of getInt immediately? Right into new pointer arrow n. And again, to be clear, if this is more clear, though I think it's a little more complicated looking, this would have been identical. Go to that location and then access the field called n. All right, so why do I then do this, do you think? It's arguably, this here might not be necessary. After all, if this thing goes at the beginning of the list, are we going to have its pointer initialized to null? No, so it's kind of a design decision, right? And at least sort of being a little overzealous in what variables you're initializing can at least help you sort of avoid memory bugs. Because again, if a variable just comes out of memory for you, out of thin air, and contains some junk value, well, going to that value might not necessarily trigger a core dump, at least not for you. But for the next user who runs your program, just by chance, it's possible that it will in fact be a problem. So generally, this idea of initializing your variables to known values, particularly sentinel values like null, good practice, because then at least you know by nature of how a computer works, if you try to dereference null, it will segfault again and again and again and again, which in the case of development time is a good thing, since you catch it then. All right, what cases do we have to handle? Well, here again is where you have to start thinking more carefully. If the list is empty, I better not try manipulating any pointers in structs, because in fact, it's very easy to insert an element into an empty list. Just remember it, so long as you've initialized its own field to null. So what that first line of code handles is the case where this thing is initially null. We've just created this guy for the first time. We've initialized it to the value 10, the null field there. If the list was empty, all we have to do is that. And we are done. So that's our first if condition. What about this? This condition says if the new pointer, so the new structs field called n, is less than the first field called n, that means this thing belongs to the left of it. So it gets inserted at the beginning. Well, per our claim of order of operations being important, we first point the next field of this new struct to be the former first element, and then we update the first pointer, the global variable, to be the address of this guy. So consistent with the picture. What else might we need to handle? Well, the else condition's a little bigger because now we sort of have the traverse function and the find function and the insert function all rolled into one because they're all sort of related at this point. So we now need to check where does this thing actually belong. Well, most of this code, even though it looks a little long, is pretty similar to what we've looked at. We've got this temporary pointer, this time called pred pointer, so I could be consistent with that guy's figures from the book. While true, do the following. Well, if the current node equals the number we're looking for, well, we decided arbitrarily this program is not going to insert duplicates. We're implementing a set, so to speak. So just quit. Free the node you preemptively allocated and just quit. Don't try inserting anything else. But else, if the current pointer's field is null, that effectively means, because we're in a loop, that we hit the end of the list. Whether the list is of size 1 or 2 or 3 or even something much bigger, if you hit null with this pointer, it means your finger almost walked off the end of the list. So where does this element belong? Well, this element belongs simply at the end. So if you have hit this guy, pred pointer is pointing here, and his next field is null, it's actually really easy to insert this thing into the list because the new element, which looks like this with the number 10 with the null character there, just takes on that depiction. That's all. So it seems that handling an empty list is pretty easy for insertion. Handling an element at the tail of the list is pretty easy. So the only somewhat scary case is this guy, but even then we're almost done with the function. So if pred pointer's next field's n value, so this is kind of neat, and it's perhaps the only complicated syntactic piece here. You can follow these arrows again and again, so long as you're careful and you're not risking hitting null. So if pred pointer, so say we're here in the story, we've been jumping along. If this guy's next field, n field, is what? Greater than what I'm looking for? Well, that means stop. I'm about to go too far. So if the current element is less than the one I would get to if I took one more step by following arrow after arrow, well, what do I want to do? I want to insert this guy right before him. And so these two lines of code, as you sort of claimed, some of you verbally, was the right order in which to do this, simply plugs that element into the middle of the list. And I won't walk through those lines of code, just to take faith that, or at least remember that insertion in the middle really boiled down to this. So that depiction there. And so all these two lines of code are doing, if you sort of keep track in your head, is implement that same idea. Otherwise, why do I do this if all else fails? Why do I do this? Well, this is just a case where if it doesn't it wasn't at the beginning, if it doesn't belong at the beginning, if it doesn't belong at the middle, I need to keep walking and check if it belongs in the next, between the next two elements or the next ones. And so this was our pointer gets pointer next field, but I just named the variable something different here. So let's take a quick glance. We won't bother looking at delete since it's pretty much the same idea and it's certainly a fun at-home exercise perhaps. But list2.h. So it was nice that we had ints sort of built into the struct that we were linking together. But if we want to cram now, not just a primitive like an int into this 4 bytes and a primitive into here and a primitive into here and so forth, it'd kind of be nice if we could maintain arbitrary amounts of information. And so list2.h proposes this idea. First, define a struct called student that has an ID field and then 2 chars. So for now, just think of that as like a black box. Meanwhile, now I need to store not an int inside of my node structures, not an int there, but instead I need to store a pointer to a student object, though there are different ways to do this. So the motivation for this version 2, is to cram not the number 9 and 17 and so forth, but instead, we'll just draw it like this, a box that stores inside of it a student's ID number, a student's name, and a student's house. And so again, what this is allowing us to do, this ability to just chain arbitrary objects together, is it just gives us a great deal of flexibility. And so for instance, in problem set 6 in a couple of weeks' time, one of the things you could do when implementing your dictionary is take words that might be of different lengths, 2 characters, 5 characters, 12 characters, plug them into these sort of black boxes here, but link them all together via this structure. You can be a little fancier. You can use something called a doubly linked list, which itself has various features, but per someone's suggestion earlier, actually wraps things around. Wraps things around. Nope, this does not wrap things around. You could wrap things around, but in a doubly linked list, you just spend a few more bits so that you have arrows going this way, but also this way, because that actually makes it easier to code some of the stuff we were coding before, because you don't really need a left finger and a right finger if you have constant reminders as to what's to the left and what's to the right. Or you can get fancier still and move away from structures like these, which are linear in their running time, because you do need to traverse them from left to right, because the magic we'll reveal on Monday, as well as finish up this second linked list example with students, is to show you how you can whittle a complicated data structure like this that's linear into something that gives you your answers in constant time, order of 1. So we'll see you on Wednesday for the quiz and Monday for lecture.